It's one of the strongest materials on Earth. It has changed the course of history, shaping our civilization and the way we live. Steel is the critical breakthrough behind three icons of American architecture: the Brooklyn Bridge, the Gateway Arch, the Empire State Building. But today, scientists are re-engineering steel's molecular structure, creating new forms with the potential to build higher, further, and stronger than the world has ever seen. Now, go inside the science of steel. Versatile, durable, flexible. Steel is a cornerstone of the modern world. If you think steel isn't essential in your daily life, think again.
Steel has impacted our lives in a lot of ways that we take for granted. Almost everything you use, you wake up in the morning, you turn on your faucet, you think of the toaster oven you use, but it's all steel that you're touching. The automobiles we drive, airplanes, ships, all these things are made out of steel. I would ask anyone who's not sure of the significance of steel to look around in their daily lives and count the number of times they touch steel in a 24-hour span.
The world produces nearly 1 billion tons of steel every year. This material's unique characteristics give it uncommon versatility. Steel can propel a high-rise into the clouds as easily as it keeps food preserved. Its applications are vast and varied.
Steel is a wonderful material, a lot of flexibility, and steel's design and use is only limited to the imagination of the human mind.
But before skyscrapers soar, before a surgeon wields his scalpel, or a bumper is fastened to a car, steel must be created. Unlike silver or gold, steel is not a naturally occurring element. In order to create steel, man must step in. Steel is made by changing the levels of carbon in iron. By heating iron to at least 2,800 degrees, it changes from solid to liquid. This transformation forces carbon atoms to separate from iron atoms. The result? Molten liquid. But the carbon-to-iron ratio must be exact. Too much carbon will make it hard and brittle. Too little carbon, and the steel will be too malleable and unable to support weight. The driving force behind the production of steel is the steel mill. All across the globe, mills manufacture steel that will shape our world.
Probably the most difficult thing that people may not understand is exactly how the steel product is made.
It all begins with iron ore, taken from mines and brought to the heart of the steel mill, the furnace. There, the raw material is melted down, filling the furnace with molten liquid. And then, the furnace is drained.
It takes 8 hours for it to travel through the furnace and come out the tap hole as liquid iron. Then it runs into our iron trough. Our iron trough is like a reservoir.
Once melted, it's treated with blasts of oxygen.
Where you're at right now is called the VOP shop, which stands for the basic oxygen process. Basically what happens here is oxygen is injected at supersonic speeds. You're removing all the impurities, leaving you with high purity steel.
The purified liquid steel is poured into a giant container and transferred to the ladle metallurgical furnace, or LMF. This is where the steel is customized to suit virtually any need. Elements and alloys are added to give it specific traits of strength, durability, or flexibility. Want to build a submarine to withstand 1,000 feet of water and temperatures near the freezing point? Start with tiny levels of carbon and add tungsten for maximum resistance to pressure and extreme cold. Looking for a knife to slice effortlessly through a thick steak? Add a little chromium for strong, smooth, lightweight stainless steel. Need to erect a skyscraper that can stand up to the force of 200-mile-an-hour winds? Add elements including manganese and vanadium for high strength and flexibility.
The amazing thing about steel is that there are almost no limits to it. To engineers and architects, steel is more precious than gold. When it came along, it suddenly opened up possibilities that engineers and architects could only dream of before.
Be it a chain link fence, a razor blade, or a beam for a skyscraper, every application has its own recipe. After leaving the LMF, the precise steel mixture is now poured into vats stretching 15 feet wide and weighing as much as 100 tons. These liquid-filled vessels are then transported to the caster, where steel is given its shape. As the liquid steel passes through the caster, it is collected by heavy-duty molds. Molds can cast steel into whatever a customer orders. Be it billets for an oil drilling machine, slabs for a car body, or even beams for a sports stadium. You name it, a caster can shape it.
For someone who hasn't seen steelmaking operation before, and a shape that comes out of the bottom of the caster has been described by some people as the old Play-Doh machine that our children used to play with. There's a mold that gives the steel its shape, and as the steel solidifies coming through the mold, it's going to take on the shape of that mold.
Inside the mold, the steel cools and solidifies. The once molten liquid returns to a solid, strong state and is prepared for delivery.
So the steel we ship out here on any given day could go into any school, library, high-rise, stadium, shopping mall.
Steelmaking has been honed over thousands of years. For centuries, no one could consistently heat large amounts of iron to 2,800 degrees, making early steel production unreliable. It isn't until the 1850s that English engineer Henry Bessemer unlocks the technology to make it happen. In 1856, Bessemer heats iron in a new way. He creates a 20-foot tall furnace and blasts oxygen through holes in the bottom. The oxygen causes the fire inside to surge, raising temperatures to the necessary 2,800 degrees. The extreme heat allows the iron to melt and carbon atoms to burn off. The mass production of steel is now possible.
Iron contains a lot of carbon. In order to make it steel, there has to be a way of getting the carbon out of the iron and separating the two.
Before the Bessemer converter, it took steel workers up to a week to produce a ton of steel. Now they are able to produce the same amount of steel in about 15 minutes. Almost overnight, the ability to mass-produce steel makes the material widely available. Bessemer's ingenuity comes hand in hand with the Industrial Revolution. Western civilization wants to grow, to find new ways to create infrastructure and expand. Steel could be the answer. But this breakthrough isn't welcomed by everyone. To some engineers, steel is an unproven material. The 19th century is the age of iron. Iron has given rise to the buildings and bridges that surround them. But one man's faith in steel will prove its strength to the world. This new building material finds an opportunity on the banks of New York City. In 1860, New York and Brooklyn stand on opposite sides of a 1,600-foot divide. They need a convenient thoroughfare for commerce and transportation. To span the East River, they will turn to steel. Stretching 1,600 feet across New York's East River, the Brooklyn Bridge is a landmark in engineering. At first glance, it may look like stone is the bridge's main support, but it's actually steel that gives this overpass its strength. Rising almost 300 feet into the air, just 4 steel cables suspend an entire roadway high above the water. It is a testament to the power of steel. The bridge has been a main artery of transportation and trade for over a century. But few who traverse it realize that its construction helped change the world. The Brooklyn Bridge signifies the arrival of a new building material, steel. New York, 1860. The sky above the East River is empty. The cities of Brooklyn and Manhattan stand on opposite banks, separated by water. The only way across the 1,600-foot divide is by boat. But the boats that ferry commuters and commerce are unreliable. It often takes more than 3 hours to cross the river, and during the winter, frozen waters can bring traffic to a standstill.
Sometimes the river would get iced over, and ferry service would be blocked, so there was no way to get into the city.
New York needs a better solution. For decades, engineers dream of erecting a bridge to unite Brooklyn and Manhattan. But there's a problem. Constructing a bridge out of iron or stone, the popular building materials of the day, means that pillars will have to be placed in the river for support. These pillars will make it impossible for ships to enter New York Harbor from the Atlantic Ocean, crippling commerce.
They always wanted to span the East River, but it wasn't possible to do with iron or masonry.
Enter John Augustus Roebling, a civil engineer. In 1867, Roebling produces a design for a bridge many thought impossible. It will span the East River from shore to shore without blocking the shipping lanes. The secret? Steel. Roebling insists steel's relative strength can be spun into heavy-duty cables capable of suspending the enormous bridge high above the river, allowing clear passage for the ships below.
The bridge couldn't have been built out of iron because iron wasn't strong enough. Steel is double the strength of iron.
His innovative plan is met with doubt. Modern steel is still in its infancy and unproven in large-scale construction. Some engineers doubt its strength.
Engineers knew about steel, but it was entirely unproven when John Roebling first decided to use it. John Roebling was a visionary. Many people thought he was crazy to use steel.
People up to that time said it can't be done. They doubted it. The Brooklyn Bridge really gave birth to the growth of structural steel. That was the beginning.
Roebling's proclamation that a bridge suspended by steel can span the East River seems as bold as JFK promising to put a man on the moon nearly 100 years later.
The Brooklyn Bridge was a chance to either showcase steel or a chance to end steel's reign altogether.
Roebling knows that steel is the metal of the future. But the city of New York stands in his way.
People who lived in the late 19th century had a lot of experience with falling bridges. Bridges fell at an average rate of about 25 a year. It was quite courageous to suggest the use of steel.
But it's not just the fear of falling bridges. Politicians express doubt that a bridge spanning the East River is even necessary. By 1869, the political wind in New York shifts and Roebling's design is approved. Construction of the Brooklyn Bridge begins in January 1870. All eyes are fixed on the East River. It is a spectacle the city has never seen, but construction also raises a question. Is steel as strong as Roebling believes? Roebling uses 4 steel cables, each 3,578 feet long, to span the East River from shore to shore. The cables will hold the roadway more than 130 feet above the water. A series of steel vertical suspenders and diagonal stays connect the roadway to the suspension cables and hold it in place. 4 suspension cables bear the weight of the roadway. There are 19 strands inside each cable, containing 278 wires measuring a mere 3/16 of an inch in diameter. A group of 20 wires measures smaller than the head of a penny. In total, there are 5,282 steel wires inside each suspension cable. Together, the 4 cables can support more than 2 million pounds of weight, roughly the equivalent of 16 Boeing 727s at full capacity. The combined strength of the steel will make the Brooklyn Bridge one of the strongest bridges of its time. Still, a problem remains. Steel may be stronger than iron, but they share a common weakness: corrosion and rust. The deterioration that plagues iron bridges also threatens Roebling's creation. The solution is a little-known process for protection: galvanization. He encases the bridge's steel wires in a protective zinc coating. The zinc acts as armor against the elements, creating a barrier between the steel and the East River's corrosive sea air. In all, 14,000 miles of wire, enough to cross the United States 5 times, weighing almost 7 million pounds, is used in the bridge. Every one of them made from galvanized steel. Over 100 years later, the steel wire is still rust and corrosion-free. The Brooklyn Bridge stands as a testament to the innovation of Roebling's design and the material in which he placed so much faith.
Galvanizing steel makes it impervious to rusting. If those cables in the Brooklyn Bridge were not galvanized, that bridge wouldn't be here today.
Sadly, Roebling will never know the lasting impact of his steel creation. He dies in 1869, the result of an accident at the bridge site. Construction is left to his son, Washington. It will take another 14 years to ensure his father's vision is realized. Hailed as the 8th wonder of the world, 150,000 people cross the Brooklyn Bridge the day it opens on May 24, 1883. The bridge unites Manhattan and Brooklyn, but it also announces the arrival of the Age of Steel, ending doubts about steel's use in large-scale construction.
The Brooklyn Bridge served a very important purpose of convincing people that it was a viable structural material.
The use of galvanized steel in the Brooklyn Bridge is one of the trademarks of its design. Without galvanized steel, it would not exist today. But the Brooklyn Bridge is just the beginning. Today, galvanized steel is no longer revolutionary, but it is still indispensable. Its coating protects against the elements, making it highly rust and corrosion resistant. Galvanized steel has found its way into everything from cars to electrical cables.
Galvanized steel is nothing more than taking our sheet steel and dipping it in a bath of molten zinc. And that zinc on the surface of the steel is what protects your car doors or appliances from rusting. Galvanized steel is primarily used for the automotive industry, and it's used to protect those car bodies from rusting. It protects the cars from the climate, and we get many more years out of them.
Today, researchers at U.S. Steel have a new weapon in the quest to improve the galvanizing process: the galvanizing simulator. Perfecting the steel-making process inside the mill would be expensive and time-consuming. In order to save material and countless man-hours, researchers run experiments on this small-scale model.
The hot dip process simulator allows us to take small samples of steel, put them into a molten zinc bath, and expose them to the same process parameters that we would take large 40,000-pound coils of steel and do in our production facilities. The beauty of having the simulator, we could take these process parameters back to our plants and improve the plant process from what we've learned here at the simulator.
Galvanized steel may not be a household phrase, but without engineers researching and improving this steel, we would not have the mailboxes, wiring, and framing we do today. From bridges to paper clips, fenders to doors, galvanized steel is perfect for so many uses because of its smooth surface and superior resistance to corrosion. In the decades that followed the building of the Brooklyn Bridge, the use of steel spreads across America. Steel will alter the landscape by spanning great distances and making skylines soar. This metal gives engineers a new tool to bring innovative designs to life. Now, go back inside the science of steel. It towers 77 stories above the sidewalks of New York City. It is constructed from 21,000 tons of steel and rises more than 1,000 feet in the air. The Chrysler Building is a grand feat of engineering. When it opens in 1930, it stands as the tallest building in the world. But this Art Deco skyscraper's crowning achievement is not its height. It's the epic spire that adorns it.
The Chrysler Building needs no introduction. You simply walk by it or see it on the skyline, and it sparkles there like a gem.
Its trademark sparkle wouldn't have been possible without one special material: stainless steel. The Chrysler Building is one of the first structures to stretch the use of stainless steel into the world of aesthetic architecture. More than 75 years after it opens, the beautiful Art Deco pinnacle shows no signs of wear. None of its 4,500 stainless steel sheets have ever been replaced. They remain a shining example of this steel's unique molecular properties. Sleek, sterile, resistant to rust or corrosion, and, as its name implies, nearly impossible to stain. Stainless steel is the gleaming vision of modern steel. Its origin starts small and practical. England, 1912. Metallurgist Harry Beardsley is searching for a way to prevent gun barrels from corroding after repeated firing. When he combines the element chromium with precise levels of carbon, the result is a steel that resists tarnishing and erosion. The secret of stainless steel lies in a film of chromium oxide that encases it. The film is generated when low-carbon steel is combined with chromium and exposed to oxygen. The film gives stainless steel its powers of resistance. It even has the power to repair itself. If the film is scratched, the exposed chromium quickly reacts with oxygen in the air to rebuild its protective layer. Unlike the galvanized steel found in the Brooklyn Bridge, stainless steel is not a coating. It is a unique type of steel. Stainless steel's resistance to rust and corrosion has improved life in the 20th century. From everyday items that don't decay after repeated use, to the tools of modern medicine, stainless steel makes many things possible. It's ideal on the small scale, but since its invention, steel has been called upon as a tool of construction. And stainless steel will prove that it is up to the task of being the building block for a new type of architecture. Completed in 1965, St. Louis's Gateway Arch towers over 600 feet in the air and casts an epic shadow across the American plains. This shimmering beacon is more than a monument to westward expansion its designers envisioned. It's also a testament to stainless steel's potential as an architectural aesthetic. 1963. Engineers and architects want to push the use of stainless steel beyond the spire of the Chrysler Building. They get their chance on the banks of the Mississippi River. They will put this glimmering steel to the ultimate test.
By the middle of the 20th century, people were starting to understand that steel was kind of beautiful. That if you used it in the right way, as it was used in the Gateway Arch, that it was very aesthetically pleasing.
The plan for the monument is modern and bold. Architect Eero Saarinen's design is an inverted catenary curve. 75 feet taller than the Washington Monument and over 300 feet taller than the Statue of Liberty. The arch will sweep 630 feet into the air, making it the tallest monument in America. But unlike any of those monuments, the Gateway Arch will have no internal skeleton, no support beams, no trusses. The arch will be fashioned from two simple steel skids. an internal skin of carbon steel, and an external skin of stainless steel. The steel skins are individually fabricated into double-walled triangular sections, with 3/8-inch carbon steel on the inside and 1/4-inch polished stainless steel on the outside. 142 of these steel triangles will give shape to the arch. Each triangular section is made up of 18 sheets of stainless steel. Just these 2 layers of steel, along with the concrete fill at the base and a few stiffening rods, is all that will provide support and strength to the massive arch.
The lack of an internal skeleton was something very new in engineering and in architecture at the time. There were just a handful of engineers in the country that really understood the type of design that went into it.
As construction begins, skeptics suggest that the design is flawed. They question whether 2 slender skins of carbon and stainless steel can support the arch. But Saarinen knows better. Constructing the arch out of iron would make it far too heavy for it to stay up. And stainless steel's unique reflective aesthetic makes it the perfect material to create the arch. But as the arch goes up, builders face a unique challenge. The advanced design of the gateway arch has a shockingly small margin of error, 1/64th of an inch to be exact, about the width of a sheet of paper. If surveyors are off by more than a hair, when the final piece is installed, the 2 sides will not meet. But taking measurements proves to be difficult. The stainless steel is so thin that it heats up very quickly in the sun, causing the legs of the arch to expand. This could spell certain disaster for construction of the arch, so the engineers come up with a clever solution.
Precision was really the key when they were building the gateway arch, and the sun would actually heat up one of the legs of the arch and deflect it a little bit. And so to make sure that their measurements were accurate, they did them in the evening when it was cooler.
On the last day of construction, workers are met with a final challenge. The day starts out at a cool 40 degrees. But as the sun beats down on the south leg of the arch, the steel begins to heat up and expand. So much that engineers worry it will warp before they can set the last piece. Workers quickly hose down the steel with cold water in an attempt to keep it from expanding. The stainless steel is cooled, and on October 28, 1965, the final keystone section is put into place. The arch, doubted by so many, gleams proudly in the sun.
When it was first proposed in the 1940s, most people said it can't be built. And then it became kind of a local joke. It eventually took over as the symbol for the city of St. Louis.
This city's symbol has become one of the most popular tourist destinations in the world. Beyond the stainless and carbon steel skins, the arch houses a steel tram, which transports 6,000 people to the top of the arch each day, offering a unique view 630 feet in the air. With over 900 tons of stainless steel, enough to make more than 14 million pieces of tableware, the arch stands as a testament to the innovative use of steel.
The visitors who come here are kind of blown away to think that the material they're seeing on the outside of the gateway arch is the same thing that's on their dinner table with their forks and knives and spoons.
From the dinner table to the operating table to the gateway arch, stainless steel is one of the rare materials that embodies both form and function. Steel serves as the backbone for some of the most amazing architectural achievements in the world. But to see its most dramatic effect on how we live and work, simply gaze up at any skyline in any major city. Without steel, the iconic skyscrapers that reach for the clouds would not exist. And the structure that laid the groundwork for it all remains one of the world's most famous skyscrapers, the Empire State Building. It ascends 102 stories to a staggering 1,250 feet above New York's Fifth Avenue. But it's not the height of this epic tower that stands as its enduring legacy. It's the revolutionary way steel is employed to construct it. January 1930, New York architect William Lamb unveils a plan to erect the tallest building in the world. It will stretch nearly a quarter of a mile above the heart of Manhattan. To propel a building to such heights, engineers need a solid construction plan. They turn to a simple, prefabricated steel grid. To provide central strength, 12 massive steel columns will run the length of the building. For ease of construction, the steel beams for each of the 102 floors are designed to similar specifications, meaning each floor resembles the next, and the beams will fit perfectly together.
The Empire State Building went up like an erector set, and this allowed the builders to do almost what Henry Ford was doing, or had been doing, with his Model T. The columns and the beams joined very easily, and each floor replicated the floor that came before it.
Construction begins on the corner of 34th Street and 5th Avenue on the morning of March 17, 1930. To create the building's internal steel grid, 57,000 tons of structural steel will have to be molded into 210 uniform columns. Only the steel capital of the world, Pittsburgh, could fill an order this big. The steel beams molded in Pittsburgh must be transported to New York quickly in order to build the skyscraper fast and cheap. Engineers design an amazing assembly line of trains, barges, and trucks that span more than 350 miles and 3 states. From Pittsburgh to construction site, the entire process takes just 80 hours. Legend has it, when the beams arrive, many are still hot to the touch. It's perhaps the most efficient production of steel the world has ever seen. Once on site, the steel is immediately raised and riveted into place. Beam by beam, floor by floor, the Empire State Building is erected at breakneck speed. Pedestrians 1,000 feet below marvel at its rapid rise.
The Empire State Building went up phenomenally fast. The average rate of buildings before that, and even today, is about 2 stories a week. The Empire State Building averaged 4 stories a week, and at some points 5 stories a week. It's never been matched.
Just 13 months after construction begins, workers rivet the final steel beam into place. A simple steel grid has given rise to the tallest building on Earth, and one more durable than anyone imagines.
During World War II, an airplane hit it, and the building took the impact rather easily. It was a sign to people, not only that the Empire State Building was very strong, but a pretty good sign that steel skyscrapers were very strong structures.
In the 75 years since the Empire State Building opens, architects and engineers have constantly sought to refine the process of steel high-rise construction, continually searching for new ways to make buildings stronger, safer, and more efficient. One of the latest advances in steel construction is just 20 blocks from the Empire State Building. Composed from more than 10,000 tons of steel and stretching 46 stories into the sky, the Hearst Tower is one of the newest landmarks in the New York City skyline. In 2001, the Hearst Corporation decides to revamp its 80-year-old 6-story headquarters into a modern tower. But there's a problem. Directly to the west is a 50-story residential high-rise. If they build a standard skyscraper, offices on the west side of the building will look directly onto a brick wall. But they can also erect the building another way, with an offset steel core. In typical high-rise construction, a building's core, which houses elevator shafts, bathrooms, and service areas, is set in the center to bear the load evenly. A centralized core also allows for views on all 4 sides. But with views to the west already blocked, architects opt to set the Hearst core on the west side of the building. But an offset core means the building's weight will be unevenly distributed, so engineers turn to a revolutionary triangular construction design to support the building. It's called the diagrid. Their solution looks like a series of simple triangles, but it's actually a system of intricately connected steel diagonal beams that run the perimeter of the building to support the uneven weight of the tower. The diagrid provides the same structural support as a traditional internal steel grid. But with the diagrid, the steel skeleton is on the exterior of the building. This external diagonal construction also has a huge economic benefit. It requires fewer steel beams, allowing builders to save 2,000 tons of raw material. But the diagrid is not just revolutionary on the outside of the building. The design also has a huge impact inside the Hearst Tower. With no internal structural beams, there is unobstructed floor space throughout.
The Hearst building, because it's not dependent on columns, offers a wide election of floor space in the building, a lot of openness.
There is no vertical elements, so diagrid are the only elements that providing vertical as well as lateral stability for the tower.
This unique skeleton is a major advancement in steel construction. It takes the internal structure of a building and makes it part of the aesthetic design on its exterior.
The diagrid system on the Hearst building is the first time it's been used in New York City. The diagrid system is very unique, and you don't normally see this type of steel framing system for a high-rise office building.
But the diagrid is not the only ingenious use of steel in the tower. The lobby displays steel at its strongest. The Hearst's old 6-story headquarters is a historical landmark. It could not simply be knocked down to erect the tower. Architects choose to incorporate it into the new building. They turn it into the lobby and atrium of the new high-rise. Engineers employ several massive mega columns of steel for support. The beams literally brace the 850,000 square foot tower on top of the historic building.
Mega columns are made up of 3-inch thick steel plates, 3 foot by 3 foot square box columns. Mega diagonals are the diagonal columns that really brace the core of the building from the 3rd floor up to the 10th floor and give the architect the advantage to create that open atrium space.
The Hearst building once again displays steel's ability to revolutionize construction.
The beauty of it really has attracted everybody's eye in New York. And that's very innovative, and it is showing a new way to build a building.
For more than a century, steel construction has evolved to erect buildings that are stronger, higher, and pioneering. Now, go back inside the science of steel. At the University of Virginia, materials scientists Gary Shiflett and Joseph Poon are developing a new type of steel. It is stronger than anything that has come before. Darva glass is made by combining iron and carbon with various elements, including molybdenum and boron. Darva glass is something completely unique. It is an amorphous steel. In traditional steel, atoms are packed together like crystal. They have a uniform molecular structure throughout. But in amorphous steel, atoms are packed randomly like glass, meaning each cross-section is different than the one before it. This jumbled atomic structure produces a stronger steel. Like the invention of stainless steel nearly a century before, Darva glass is a potential landmark.
Until this steel was discovered, most people felt that steel development had been exhausted. What this new steel does is flies right in the face of that and shows that there are revolutionary improvements that have been obtained, and they exist now.
But Darva glass has a crucial flaw. It's brittle. While most traditional steel has the ability to expand and contract under force, Darva glass does not. It can't bend. When it encounters extreme force, it simply breaks. Shiflett and Poon are hard at work to correct this limitation.
The brittleness is a bit of a mystery, and so Joe Poon and I had to work on the science of these materials, which elements to add so we can change the chemistry but preserve the high strength and also try to get some ductility or damage tolerance in these materials.
If they can find a solution, the potential of Darva glass could be limitless.
These materials can make buildings that are stronger, bridges. They could be made longer without supports where high strength is needed or high corrosion resistance needed, and they will be commonplace.
Could Darva glass bring new skyscrapers that will dwarf the Empire State Building? Could it provide strength for bridges to span unimaginable distances? Will this new material revolutionize the world? Some believe it has the potential. Even now, in its limited capacity, Darva glass is already searching for applications. It is currently being tested at the Yucca Mountain Repository as a possible sealant for nuclear waste containment.
This new steel has great future. We can see that it will replace all the conventional steels. If it's not in 1 decade, it will be in 2 decades.
It has only been 150 years since Henry Bessemer made the mass production of steel possible. In that short time, steel has reshaped human civilization. From epic architecture to those seemingly ordinary items we take for granted, the steel revolution has stretched the possibilities of human imagination and redefined our lives. Today, at the dawn of a new century, the steel industry is responding to the demands of our future.
The steel industry 20 years from now will also be markedly different from the steel industry of today. We're constantly working to reduce the amount of energy it requires to make the steel and also to find ways to recycle and reuse the byproducts of the steel making process.
The one constant about steel is that man drives steel to continuously evolve. And if we've learned anything, it's that the story of steel is far from over.
The innovative design and the innovative uses that we have found for steel is one of man's greatest achievements.